you've seen. First of all, you start the remote client. So here I'm running on Windows. This is the thing you need to see. Then you will need to configure, so you do a configuration. Sorry. You need to configure the connection. This is what you need to set up, okay? So you choose where you want to SSH. So normally you should do a hop on Ella, so you will put your username at ella.cscs.ch, whatever. Then you will enter Daint. You do not need the username at this stage because it's the same, so you can just do this. You specify the path to Allinea DDT, and if you want, you do not necessarily need this. You can also make sure that the remote script is initialized, which means that you do a source of the init env that is included in the exercises. I'll remove it for now. This is not needed, I think. So once this is connected, you can do a test of the remote launch, verify that the connection is successful, enter your password, and everything should be all right. If you do not want to use the remote client, that's fine. We will see how to start DDT later, but it doesn't change anything, really, apart from this particular step.
So the big advantage is that it's faster. Okay? So basically what you're doing here is you have the viewing, which is local, okay? Starting on your phone. So instead of sending X stuff to the network, it has latency when you want to click on it, but it doesn't come up immediately. Normally it's much faster here. So it's much more convenient. What you can do the module, definitely. And no, it's different. You follow to that one, 3, 5, 5. Yeah, so you can, just this part. Normally to the module node DDT as well. This has to be done on base. Should be working. So now that you have the client that is started, and you want to start an application with DDT on the cluster, all you have to do is click on run, and in this window, and you specify what application you want to run, blah blah blah. And to do this place somewhere. Now everything you see is so yes. So in this case, so for proportion itself. No, you can't download this version because the version I'm being is the beta version, the next release, so the official script won't work. Normally, Debugging has a remote client with the current version. Sorry? Yeah, that's what we want. Well, we're in a debugging course, so we won't bug. Yeah. Yes. Because I didn't know what everything will do. Okay, so for people who are starting with the remote client already, you have to choose, when you click on run, you have to choose the template file. So this is something that you do once and for all. So when you're starting, obviously the remote client will need to submit the job to the workload scheduler. Okay? So in order to do so, okay, in the configuration part of the workload scheduler, here, if you click on this configure button, you will arrive to this screen. And the template file you're looking for is this one. So it's in the template directory, it's called Cray-CSCS. This will ensure that when you're starting the remote client, the job will be submitted to the queue and will actually start the configuration. Okay? What? Definitely. And I don't think it's related because it's just a matter of putting systems the type of thing doesn't matter. I think this is some other issue with that's of the reference. You're critical. Oh, really doesn't. Yeah. Not even sure we have a match definition on the left. We've tried it to be honest. Okay. Is everything working? Okay. Okay. The reason for this is because the environment is not loaded. So in this case, I would go back to the remote mode setup configuration. I would add here, so you put the part to remote script and you make sure it's source and contains the environment. Because maybe you would back asking the environment to be updated so that needs to late people to get to the website. So can you show me the it's compiled? Okay, so it seems that the same problem for everyone, so I'll go to the thing. So, if you have an issue, because Allinea DDT is asking you to start with MPI and you can't see MPI here, it used to be, I don't know why it's not, but it should be. So if you go to Configure, in System, there is a list of MPI libraries that is available in the option. So you select the Cray XC30 library. Okay? And if you validate, you put an OK somewhere. Now you should have a certain amount of processes that is available. There is also another option that you need to change for this library, the job permission. Please do not use one customer. Change this value to specify in the run window. Is it okay? Better? Yeah. System. To avoid the difference don't know the password. problem? Okay, so if you go to the printer, remove the tab. Just do it there. So it's running, but it's not running. So this is using the remote phone. It's good so far. For this one, this is going to cut the load, otherwise we'll be using phone. No, don't do that. So now you don't have this, okay? And you can see the reload instead. Now you can see some. You can stop and take out the one so you can install. And you will go through 8 steps otherwise you will have to. This is a recently course. This is system number. It's done in the system number type 2. So now you can someone is using a big thing. Someone is doing a big debugging process. Just control and try them in everything starting to do stuff. When you start to control things. It's okay, but it's not that hard. Not at the moment, but you're not the first one to ask. So there is an environment variable that's going to be so you can have to stop DDT at the moment. Well, you can have DDT to stop a function name, which is really the function. Well, it's not the default behavior, it's stop at the function. Yeah, well, we discussed this with no here, but I think that the server documentary in the Cray library, the following documentary is how you do that. More likely that there is wrong argument or wrong arrays or something weird in there, rather than controlling it in the people. It's possible. So, yeah, I think one of the boundary bodies. Do it. Yeah. You not doing industrial coding. Yeah. Okay, right. Well, it reduces the simulation. So it's exactly the same. The only difference is here now we're using it as well. No, I just want to go for the license. When you click on submit, you click. By default. Yeah. So, so you have, well, several button steps. So you have root, button, step. If you focus on root, it means that you will focus on all the processes on that one. You have multiple bits. You can do right click. Okay. So if you move to process, in this case, if you click on step, and this will only be the process 2. So that's it. You move forward, not the rest. If you click on thread, so assume that you have multiple, this is assuming that you have multiple steps of processes. So you can think of it. I've never tried it. here. Is there anything to do with this one except taking back? No? Can you fix it? Yeah, that's the point. If you want some time, try to without the hand, without reading it. Wait, just stuck in it. What you can do is if I see that focus on this without the hand. Okay, well, you need something for the work. because there is an HTC. Which means that there's a trap. Okay. Ah, no, right. So this is what. Okay, so I think that the application is just finished. Anyway. So you can get in the. That's another problem. You don't have any good yet. So is your environment well set? So did you do that source response? Alright, so maybe you can read it. Maybe this is well, you really want to be silent, huh? Yeah. Yeah, there is a memory bank. I'm sorry. You wanted some silence. It's not a big. Oh yeah, because you have it here. So put down. So you okay? No. So you have to definitely memory. And basically this is extremely important because if you quit, you lose your submission. Whereas if you go restart, you keep your node and you just restart the job. Very good. Okay, so did everyone find the first bug in the first example? Okay, let's have a look. Okay, so let's do this. Let's do this first bug. Let's Okay, so I compiled my application. So the first thing you need to be aware of is that when you have an application that you want to debug
with Allinea DDT, there are a few options that are absolutely necessary. The first one is -G. If your code is not compiled with -G, you won't be able to debug it. And the second is about the optimization options. You can use whatever optimization option you want. You can use O3, inlining, whatever. Keep in mind that if you do so, the compiler will optimize things, which means that some variables that you think exist in the source code actually do not exist in the binary. You may find out that when you click on step, the code is jumping from one line to line 10. That's because some code has been inlined, which means it's not executed in the same way. So it's not the debugger, it's just the way the binary works. So if you have some issues that happen with a high level of optimization and you can't reproduce with O0, then that's fine. Keep your optimization options, but if you can, use O0 because you will see more things, you will see more values, more variables in this setup. So once this application is compiled, we'll just run it on a few processes on the code, see what happens. So if we do a sbatch run me, my code is running, it stopped, there is a core file that has been created, and we can see in the output that there has been a segmentation fault somewhere in the code. So at this stage, what you want to do is to try to debug this. So instead of putting printf, print statements, and trying to do stuff with the code, what we will do is just execute this application with Allinea DDT. Okay, so you've not seen this. So I connect with my light client. So I'm connected on my cluster. I choose to run my application when this comes up. There you go. So I'm moving to exercise 1. I want to run this code. I can add a few arguments if I want, but for this, we'll just keep here. Run on 8 processes, on 8, on one single node. You can activate OpenMP if you have an OpenMP code, CUDA, etc. You submit the job, and Allinea DDT will automatically submit the job to the workload scheduler and will be running on the compute node. Okay, so it's doing the same thing that it was doing to you earlier. So we'll try again. Otherwise, you can also start with SSH-X. That works too. Okay, so we'll start with SSH-X. At least that will work. No change here. I'm submitting my job. So now Allinea DDT is attaching to the different processes. Okay, there we go. So you've probably, well, have a good overview of the GUI now, but basically at the top of the window you have all the controls, which is play, pause, step, etc., etc. Those controls apply to a focus. So the focus is the target. So for instance, now if I click on step, my focus is the group, which means that all processes in the group I have selected will move forward. So if I click on step, you can see that the code has moved to line 90, and this applied to all processes. If you want to control one specific process and all its threads, or if you want to control one particular thread, you can change the focus here, and the order that you will give will only apply to the current thing. So for instance, here I applied a step order on process 0. If I move back to my old focus, I can see in the stack that one process is in a different location than all the 7 other processes. Anyway, so from there, you have different parts of the screen that are available. On the left-hand side, you have your project files. This is your source code, basically. In this case, it's very simple. There's only one file, but you can imagine much more complex environments with lots of files, lots of lines of code. In this case, you can browse this, this project just easily. So if you're looking for a particular function, everything is indexed. So if you start typing it, for instance, you click enter on print arg, in the source code browser, which is in the middle, you will automatically jump to this particular function that you have been looking for. On the right-hand side, you have different tabs. The first tab is the locals. So this is the picture of all the variables that are local to the current context. And you also have what we call the current line, which, depending on what you select, for instance, I'm selecting this line or I select the other line, will only show the variables for this particular line. Does any of you has an idea about what this line is? Next to the variable? Oh, but you don't have the right to answer. Yes? Yes, correct. So this is the perfect answer. So when you look here, you have a flat line in the middle. This means that for all the processes, the value of this variable is 100. So you don't need to change the process and say, okay, what's the value for process 3? Okay, so let's be here, so we won't change the variable. So let's look at the variable on process 3, on process 5, etc. This is not necessary. You have the global picture. If you click on the picture, you will have, well, the same information. Okay, so it's saying value 100 for process 0 to 7. If we step the codes, we are here forward. You see here that we have the rank, which is a diagonal. This is a linear distribution, which means that for process 0, the value is 0. For process 1, it's 1, etc., etc. Okay? So it makes it easy to understand, if you're running in parallel with lots of processes, how the variables are distributed. So now we have our code. When we run it, we realize there was a crash. So if we run the code again, when there is an error that comes up, Allinea DDT will catch this error and will tell you, okay, so your processes 4, 6, 7, whatever, have crashed on line 108 and they had a segmentation fault. So you can see here now that we have different colors in the processes. So there are some processes that are in green. This means that they are running. If the processes are in red, they are paused. The processes that have been paused now are only the processes that have crashed. The others are still running. So if you want to stop everybody, you click on pause, and that's it. So what you can see here is, first of all, look at the stack. Always look at the stack, because this is where things get interesting. We have 3 groups of processes. One group of processes that are stuck in the MPI finalize, so these ones are fine. We have one process that is in the MPI receive, so it's fine as well, he's waiting for someone. But we have 3 processes that crashed on this particular line. Okay? So I know that you had a look on the different problems. Did you find out what the bug was? So what the bug was? What was it? Yep.
Well, comparison because you are adding something plus my rank plus 1, and it is just it is 0 modulo 12. It will eventually outrun the
Mm-hmm. Yeah, so this is correct. So basically what happens in this loop is you have a y variable that starts as 0, and every step you add the rank plus 1. So if we take, for instance, process 7, well, at the first step it will be 0, then it will be 8, then it will be 16, which is over the boundary, which means the loop will continue forever until it crashes. So to validate this, there are multiple mechanisms. What we can do is use, for instance, trace points. So to use the trace point, what you do is, well, you select your line, you create a trace point in the relevant tab, so you do add trace point. You say that you want to print variable x and y forever, and you want to record 3 values, so 3 steps in the loop. So if we do this, there is a green icon that is present here. Okay. Now, in order to restart the job, the thing that you do not want to do is quit DDT and re-go through the submission and everything, because it means that you've lost your nodes and you're redoing a submission. So what you can do is restart session. This means that the current job will be killed, but you do not go through the allocation process again. You're just using the nodes that you had before. So by doing this, the code restarts immediately. And there you go. So the trace point is present. I can add a breakpoint by clicking here as well if I want. I run my application. So I have my breakpoint that is reached. I have my segmentation fault. And the trace point output is present in the appropriate tab, which is next to trace point. So here you can see that we have recorded the value of my variables for my group of processes. So we have the small picture that represents how this is distributed. And this is ordered by step, by group of processes, and it comes, well, in order, which means that you don't have a messy output that like you would have by doing a print statements. And you validate here your theory that after the second step, you can see indeed that the y variable, the upper limit of the y variable is bigger than 12, which means that you're out of bound, you have a problem. Okay? Is it clear to everyone? So I mentioned the logbook earlier. So this is the tab that is next to this. Imagine that you clicked too quickly on an error message and you can't remember what it was. If you go to the logbook, you will find out the history of what you've done. So when you had the segmentation fault, the stack was this one. You had also the variables, the outputs, you had the output of the trace points, etc. So everything you do in the GUI is recorded, and you can save this file in an HTML format. So this is the first bug. Do you have any question about this one? No question? Clear? Okay. So there is a second bug in the code. This bug was added if you had arguments, for instance. So let's start on 4 processes, smaller scale. Does anyone want to correct it for me? Yes. Come on. So I invite you here to debug in front of everyone the next problem. Huh?
That one with the argument. Have you started it?
Yes, it started with arguments.
Okay, then now just run it.
So this was the breakpoint I had.
Okay. Okay, now stop. Okay, there is no source for
Okay. So just a small, if you have this kind of window, it's fine. It just means that the file that Allinea DDT stopped in is a file that has not been compiled with -g, which is normal. Here we are looking at some system code, so it's fine. But if you go to the stack and you move up, at some point you will go back to your user-defined code and you will be able to see the source, okay?
Okay, and then here one sees that this the argument passed to this print arg function, which is supposed to be a string, is clearly out. It even says here it's out of bounds. It doesn't make sense. It's not a string pointer. So yeah, we have to go up one more level, and then yeah, one notices that here obviously there is a typo. The loop variable was supposed to be x, but here and also in the arrow indexing there is suddenly a y, which shouldn't be there. So if one changes this, then one gets a loop which runs from 0 to argc, which is correct, and y is pretty much random. It's not reset after the previous loop, so it will eventually crash the rank 0, because okay, this is only run in rank 0, and that's why it crashes here. So okay, I can change it right now. Is there possibility to?
Yeah, sure. If you open the terminal, there's a. So if you do a Control Z first. Okay. So you can do a VI or whatever.
Change this to x, change this to x.
Okay. So if you, no, not this one.
This one?
Yep. There we go.
Stop the exit.
Success. Thank you. Is there any question? No question? Okay. So I suggest that we move on to the second exercise in this case. So if I go to the presentation, the second exercise, first one, is an open ACC code. Okay. So in this case, there are a few things that we want to do. Is first of all, learn how to debug an open ACC code. Basically, what I want to prove is that whether you're debugging a CPU code, a GPU code with CUDA, with OpenACC, with whatever, for Allinea DDT, from your perspective, it won't change a thing. It will be exactly the same. So in this case, we have an application that runs successfully, but if we run it, we realize that there is an error. So this code is, I think it's the Saxby code. So if you have a look at the handout, we'll explain to you what it does. The idea is if we execute this code like this code as it is, the output that is generated will have wrong values, wrong outputs. Okay. Yep. Interesting. Jean-Guillaume. Normal. Ah oui, tiens. Thank you. Right. So when we look at the output, well, we realize that this code has been executed on 2 processes. For the first process, well, the output looks good. For the second process, the output is 0. There is no crash, but the results are wrong. So why are they wrong? And this is what you will try to figure out now.